Hello everybody, welcome to the last topic as part of this NPTEL course on material and energy balances. Today we will be talking about unsteady state material and energy balances. Until now all the processes that we have looked at are at steady state. So, we have always assumed accumulation to go to 0. However, under certain special conditions this does not have to be true. So, in some cases like batch systems or semi batch systems or continuous systems during startup and shutdown, the processes would be unsteady. So, we have to account for the accumulation term as well when we perform material or energy balances. Today we will see how to perform such unsteady state balances. So, here what happens is the quantities or the operating conditions within the system will be changing with respect to time. Because these parameters are dependent on time, they are unsteady state. They are also called as transient processes. So, these complex systems are actually more tedious to solve compared to steady state processes. Unsteady state processes in the industry could be seen in batch or semi batch processes or continuous systems during the startup and shutdown. So, when the system is fully operational, they usually operate at steady state. However, every year or every month, depending on the size of the company and the processes might be shut down and started up again. So, during this initial phase of startup and final phase of shutdown, you would be experiencing unsteady state processes. There can also be unsteady state when one of the process condition is being changed to another. Also, if there are fluctuations in the input or control variables, you might experience unsteady state processes. So, before we start solving unsteady state problems, let us visit the general balance equation. So, the general balance equation which we have been using throughout this course is given here. Accumulation equals input minus output plus generation minus consumption. So, in this equation we have always assumed accumulation to be 0 when the process is steady state. Until now we have always ignored that term. We have only worried about input, output, generation and consumption. Generation and consumption terms had to be calculated only for reactive processes, and if we had total mass balances, then generation and consumption went to 0, and also for non-reactive components. Input and output are the terms which we almost always calculated. In some cases those were also going to 0 if you are talking about closed systems. Okay. So, now let us look at how this equation would be for a mass balance. So, for material balances, mass accumulated is equal to mass entering minus mass leaving plus mass generated minus mass consumed. So, if we were to take the following system, which is a continuous system with m dot in as the inlet mass flow rate, m dot out as the outlet mass flow rate, Rg is the rate of generation of a component and Rc is the rate of consumption of a component, then we can actually write general material balance equations. So, in these parameters, until now we have assumed that none of the parameters will change with respect to time. However, in an unsteady state material balance, these parameters can actually change with respect to time. So, to account for that, our balance equation would have to be considered for an infinitesimally small time interval. So, if you take delta t as an infinitesimally small time period between time points t and t plus delta t, then you can assume that the system variables are a constant for this particular small period. So, even for an unsteady state process, we can assume constant system variables for very small time periods. So, using that we would actually be able to calculate the mass entering, mass leaving, mass generated, mass consumed within this time period as the rates time the time. So, if we were to calculate mass entering, it would be m dot in, which is the rate of the mass flow rate for the inlet stream, times delta t, which is the time period which we are looking for. So, it will be a flow rate times time. So, that will give you the mass which is entering into the system during the time period delta t. So, that is m dot in delta t. Similarly, mass leaving during the period delta t is given as m dot out delta t. Mass generated is given as r dot g delta t and mass consumed is given as r dot c delta t. So, now that we have these terms, we can plug them into the general material balance equation we had. However, we still have to account for accumulation. So, accumulation is nothing but change in mass over the period of time. So, we can assume delta t is the change in mass inside the system during this period delta t. So, this delta m is the accumulation. So, substituting all these in the general material balance equation we had, the equation becomes delta m, which is accumulation, equals to m dot in delta t, the inlet stream, minus m dot out delta t, the mass of the outlet stream, plus r dot g delta t, which is the generation term, minus r dot c delta t, which is the consumption terms. If you were to divide the entire equation by delta t, then you would get delta m by delta t equals m dot in minus m dot out plus r dot g minus r dot c. As delta t tends to 0, basically as delta t becomes smaller and smaller and becomes completely infinitesimally small, then this equation can be further modified to dm by dt equals limit delta t tends to 0, delta m by delta t equals m dot in minus m dot out plus r dot g minus r dot c. So, the differential balance equation for an unsteady state material balance would be dm by dt equals m dot in minus m dot out plus r dot g minus r dot c. As long as any of the term varies with time, the differential on the left hand side, which is dm by dt, is non-zero. So, if all of them are independent of time, then your accumulation will go to 0 and it becomes a steady state process. For unsteady state processes, one of these 4 components which you see on the right hand side, input, output, generation or consumption, is actually dependent on time. There could be more which are dependent on time as well, but at least one has to be dependent on time. If that happens, then the process is unsteady state and dm by dt cannot go to 0. To solve the differential balance equation, you need a boundary condition, right. So, because it is a first order differential equation, and to solve this you need at least one boundary condition, usually an initial condition where m at the time t equals 0 is given. So, once you have this information, you can actually solve the differential equation which is given here. So, here is an example problem which will help us construct such differential balances for the total mass and for a component A. So, the problem statement says a continuous stir tank reactor is used to produce a compound R in the liquid phase reaction A gives R. Feed enters the reactor at a rate of V naught dot liters per second. Concentration of the reactant in the feed is Ca naught moles of A per liter. The volume of the tank contents is V in liters. The vessel may be considered to be perfectly mixed. So, the rate of consumption of A is given as kCa moles per second liter, where liter is the reaction volume. Assume all fluids have the same density rho. So, basically density is not changing. You are asked to write the differential balances on the total mass and moles of A. So, let us try to write this differential balance. As we have always done, the general balance equation we would have would be input minus output plus generation minus consumption equals accumulation. So, if we look at this equation, we have been asked to write the differential equation for differential balance for total mass and moles of A. So, let us first start with total mass. So, for total mass you would have generation and consumption will go to 0, as mass can neither be created nor be destroyed. So, this would mean you are left with input minus output equals accumulation. So, once you have this equation, we now have to account for the mass which is entering into the system and the mass which is leaving the system. So, the total mass which is entering the system can be obtained by the volumetric flow rate multiplied with density. So, that would be V naught dot times rho giving liters per second times grams per liter, which would give a mass flow rate of grams per second, and your output stream would be V dot times rho. So, here V dot is the volumetric flow rate in liters per second and rho is density in grams per liter, giving you grams per second, again a mass flow rate. So, now the accumulation term has to be accounted for. The accumulation term would be dm by dt. So, this m is the total mass of the components inside the reactor. So, how do we account for this m? So, that would be equal to rho times V, where rho is the density and V is the volume in liters of the reaction mixture inside the reactor. So, now we have this. So, the equation then becomes V naught dot rho minus V dot rho equals d rho V by dt. So, where rho is actually a constant, so it can be taken out of the differential. So, it will become rho dV dt would be equal to V naught rho minus V dot rho. So, the rho can be cancelled. So, the equation becomes dV by dt, which is the change in volume with respect to time, is equal to V naught dot minus V dot. So, this is the differential equation. From here we have to get, we can solve the equation only if we have the initial condition. So, what would be the initial condition? At time t equals 0, V should be equal to capital V naught, which is the volume at time t equals 0. So, this would be the differential equation with the initial condition. The next aspect of the question is to solve for the differential balance for number of moles of A. So, let us try and do that. So, we are trying to write a balance for moles of A. So, this would have input minus output plus generation minus consumption equals accumulation. So, here only generation term will go to 0 because A is a reactant and not a product. You have A entering the reactor, so you have an input term, A is leaving the reactor, so you have an output term, A is being consumed by the reaction, so there would be a consumption term, and accumulation would be happening because it is an unsteady state process. So, in the input term we would have to calculate the number of moles of A which is entering the reactor. So, earlier we multiplied density with the volumetric flow rate to get the total mass entering the reactor. Here we are interested in knowing the number of moles of A which is entering the reactor. So, which would mean the rate at which the volume is entering, the volumetric flow rate times the concentration can give you the molar flow rate of A into the reactor. So, you would have V naught dot times Ca naught will give you moles of A per second. Similarly, for the output term it would be V dot times Ca. So, the next term would be consumption. For identifying what the consumption would be, you would have to go back and see what the rate equation given was. So, the rate equation was given as Kca. So, your consumption term becomes K times Ca, and if you were to look at the units for the consumption term, it was moles of A per second liter. So, to convert this into the number of moles of A consumed per second, you would have to multiply this term with the volume of the reactor, which is V. So, with this you get the consumption term. So, the last term you have to look for is the accumulation term. So, the accumulation term would be dNA dt. I am using N instead of M because I am using number of moles. So, this number of moles of A can be calculated by multiplying the concentration of A inside the reactor times the volume. So, this would be dCA times V dt. So, what you would notice is both for the consumption term and for the accumulation term, I have used Ca, which is the concentration of A which is leaving the reactor. So, this is because we have been told that the system is perfectly mixed. That means that the concentration of the outlet stream would be equal to the concentrations in the system. So, that is why we are using Ca, which is the concentration of the exit stream for A as the concentration of A inside the reactor as well. So, now that we have this, the equation can further be simplified to get V dCA by dt plus Ca dV by dt equals V naught dot Ca naught minus V dot Ca minus Kca V. So, this would be the differential equation. Now, we also need to write what would be the initial condition. So, at time equals 0, we do not know what the concentration of A would have been. So, we can just say C equals Ca of time 0. So, this would be the initial condition. With this, we have the differential balance equation for number of moles of A and the initial condition. So, in the previous example, we looked at how to write the differential balance for an unsteady state process. So, this was the differential balance which we wrote. So, to solve this differential balance, we would have to rearrange this equation and integrate it. So, the above equation can actually be rewritten as dm equals m dot in dt minus m dot out dt plus r dot g dt minus r dot c dt. So, this can then be integrated between the limits of initial time t naught and final time Tf, and when you do this integration you will be able to solve the equation. So, while you are integrating the equation between the limits t naught to Tf, you will get this equation which can then be simplified simply called as the integral balance. So, once you know how these terms are actually changing with respect to time, you can plug in these functions into this equation and solve for the unknown. So, this is called as an integral balance. Let us try an example problem which will help us practice how to get integral problems, integral balances and solve for the desired values. So, here is an example. The water level in a municipal reservoir has been decreasing steadily during a dry spell. There is a concern that the drought could continue for another 60 days. The water consumption rate of the city is estimated to be 10 power 7 liters per day. The net water input rate, which accounts for rainfall and stream drainage into the reservoir, is estimated to be 10 power 6 times exponential of minus t divided by 100 liters per day, where t is the time in days from the beginning of the drought when the reservoir contained 10 power 9 liters of water. Calculate the reservoir volume at the end of 60 days of drought. So, how would we go about solving this problem? So, first we would have to write the general balance equation, we will have to write the differential balance and then rearrange it, integrate it to get the final values, which is the final volume of the reservoir after 60 days of drought. So, let us try and do this. So, as usual we would start with the general balance equation, general material balance equation, which is input minus output plus generation minus consumption equals accumulation. So, generation and consumption terms will go to 0 because there is no reaction happening. So, you would end up with input minus output equals accumulation. So, the input term has been given as 10 power 6 times exponential of minus t divided by 100, and this is given in terms of liters per day. To convert it into mass, you would have to multiply it with density, because this is water, we know the density which is 1 kilogram per liter. So, multiplying this with 1 kilogram per liter as the density, you would get this input in terms of kilograms per day. Similarly, output stream can be calculated. So, it is 10 power 7 liters per day, converting into mass, you would get 10 power 7 kilograms per day. So, the accumulation term has to be accounted for. The accumulation term is dm by dt. So, this dm by dt can be written as d rho v by dt, where rho is the density and v is the volume. So, this will become rho dv by dt, and because rho equals 1 kilogram per liter, the equation for a term for accumulation would be dv by dt. Plugging these values back into the equation, you would get dv by dt equals 10 power 6 exponential of minus t divided by 100 minus 10 power 7. So, this equation has to be solved. So, rearranging this equation we would get dV equals 10 power 6 exponential of minus t by 100 minus 10 power 7 times dt. So, integrating this equation we would get integral dV equals integral 10 power 6 exponential of minus t by 100 dt minus integral 10 power 7 dt. So, now what would be the limits for this differential? So, we know the initial volume of the reservoir before the drought started was 10 power 9. We have to find the final volume, let us call that V. So, we know that the drought lasted for 60 days, and which means that the day in which the drought started can be considered to be time equals 0, and the last day of drought would be 60. So, the time frame is from 0 to 60. So, this would be the limit with which we would have to integrate this. So, this would mean the equation becomes V minus 10 power 9 equals 10 power 6 exponential of minus t by 100 divided by minus 1 by 100 with the limits of 0 to 60 minus 10 power 7 60 minus 0. So, solving this equation, so we can actually substitute the values for t from the limits. By applying the limits and solving the given equation, we can get V equals 10 power 9 minus 10 power 8 times exponential of minus 60 by 100 minus exponential of 0 by 100 minus 10 power 7 times 60. So, you can solve this equation and you will be able to get the value for V as 4.45 times 10 power 8 liters. So, this would be the final volume of the reservoir after 60 days of drought. As you can see from these calculations, when we did the differential balance, we were able to get an equation which can actually explain the correlation between the terms which are changing with respect to time and accumulation. When we actually use the integral balance, we can integrate and get numerical values based on the limits that we apply and the initial conditions that are provided. So, we will move on to the next concept. So, when we are solving unsteady state material balances, there is a general procedure which we should follow. So, we will go through that. The first step is like for any other material balance problem. You would write the general balance equation and eliminate terms that are equal to 0. The next thing is you would write an expression for the total amount of the balanced species in the system and differentiate it with respect to time to get the accumulation term. So, for example, when we first did the total mass, we did dm by dt, whereas in the second part of the first example we were looking to write the balance equation for number of moles of A. So, we wrote dNA by dt. So, basically what you have done is you have written the total amount of the balanced species in the system and you have differentiated it with respect to time, and this becomes your accumulation term. You are asked to substitute the system variables to the other terms, basically the input, output, generation and consumption terms need to be substituted based on information which is available. If there is a function of time, if something is actually y of t is a dependent variable to be determined, then you rewrite the equation to get an explicit expression for dy by dt with a boundary condition for y at given t. So, usually initial condition which is y equals something at t equals 0 is provided to you. So, then the last step is to solve the equation analytically if possible. So, if not, you would use numerical methods to solve it. So, you can also check the solution. So, here if you were to check the solution, what you would do is you can substitute the boundary or the initial condition to the expression obtained to confirm if the known value of the dependent variable is obtained when you actually do this. Then another method can also be employed to check the solution, which is you can differentiate the solution obtained to verify if you can arrive at the initial equation. By doing these kinds of verification, you can confirm if the solution you arrived at is accurate. Last step, if required, might be to plot the solution using a graph or to build a table which will give you the values. Here is one last example for unsteady state material balances. We will try to solve this to get clarity on the procedure which we just described. A liquid phase reaction with stoichiometry A gives B takes place in a continuous perfectly mixed 10 liter stirred tank reactor. The tank is initially filled with a solution containing 2 moles of A per liter and the inlet and outlet flows then begin. Write a balance on species A and provide an initial condition. Calculate CAS, the steady state concentration, as T tends to infinity. Solve the balance equation for C of A and check the solution and plot the curve. So, here we are expected to first write the differential balance and then apply the limit of T tends to infinity to get what would be the concentration of the substance A, which would be the steady state concentration, and then the last objective is to develop an equation which would represent concentration of A as a function of time, and then we have to plot a curve. So, let us see how to go about solving this problem. As usual, we start with the general balance equation, which is input minus output plus generation minus consumption equals accumulation. So, here you do not have a generation term for component A. However, you would have a consumption term, you do have input and output and accumulation terms. So, the input term would be equal to 0.15 times 10, because 0.15 is the volumetric flow rate, 10 is the concentration of A in terms of moles per liter. So, doing this multiplication you would get moles of A per second, which is the molar flow rate of A entering into the system. So, this would become 1.5 moles of A per second. So, output would be 0.15 times Ca. We do not know the outlet concentration, so we will just call it Ca as given in the problem. So, it will be 0.15 Ca would be the moles of A in the outlet stream per second. So, consumption term has been given as 0.0050 Ca, which is the rate equation, and as we had discussed already, this has to be multiplied with the volume of the reactor to get the moles of A which is consumed within the reactor per unit time. So, this would give 0.0050 times 10 Ca. So, your consumption term is actually equal to 0.05 Ca, which would again be in terms of moles of A per second. Accumulation term, as we had already described, would basically be d times number of moles of A dt. So, it is the differential with respect to time, and this n, which is the number of moles of A, can be written as the number of moles of A which is present inside the volume would be volume of the reactor would be d times Ca times V dt. Okay. Ca is the concentration of A inside the reactor and V is the volume. Again we are using Ca in both consumption and in accumulation because the system is perfectly mixed. As the inlet and the outlet flow rates are equal, the volume of the reactor will not be changing, and the volume of the reactor has been given as 10 liters. So, this dCAV by dt can be written as 10 times dCA by dt. So, this would be the equation for accumulation. Now, substituting all these back into the general material balance equation we had, we would get 10 dCA by dt equals 1.5 minus 0.15 Ca minus 0.05 Ca, where 10 times dCA by dt is the accumulation term, 1.5 is your inlet term, and 0.15 Ca is your outlet term, and 0.05 Ca is the consumption term. So, this equation becomes dCA by dt equals 0.15 minus 0.02 Ca. So, we also need to identify what would be the initial condition. So, it has been given that at time t equals 0, the reactor is charged with a concentration of 2 moles per liter. So, the concentration of A in the reactor at time t equals 0 is given as 2 moles per liter. So, this would be the differential balance equation and the initial condition which can be used to solve this problem. So, the next part of the problem asks us to calculate the value of CAS, which would be the steady state concentration of A. So, at steady state what would happen? dCA by dt will be equal to 0. So, substituting this back into this equation, you would have 0.15 minus 0.02 Ca equals 0. So, that would give Ca equals 7.5 moles per liter. So, that would be the steady state concentration of A when time tends to infinity. For the last part of the problem, we have been asked to calculate, we have been asked to write Ca as a function of time. So, that can be obtained by integrating the differential equation. So, we had dCA by dt equals 0.15 minus 0.02 Ca. So, this would be dCA by 0.15 minus 0.02 Ca equals dt. So, integrating this equation, we would be able to solve for the required correlation. So, what would be the initial and final condition? What would be the limits? So, Ca is basically from 2 moles, which would be the initial condition, and final concentration is Ca, which is the outlet stream concentration or the concentration inside the reactor at time t, and similarly time would be from 0 to t. So, because we want to start from time 0 where concentration of A is 2 moles per liter and go to time t where the concentration of A is Ca. So, using this equation we can actually integrate and get this as the solution. You would have ln of 0.15 minus 0.02 Ca divided by minus 0.02 with limits of 2 to Ca equals t. So, this can then be further solved to get ln of 0.15 minus 0.02 Ca divided by 0.11 equals minus 0.02 t. So, from the previous equation we can get Ca as Ca equals 7.5 minus 5.5 times exponential of minus 0.02 t. So, we can verify this as well. All we need to do is differentiate this equation or substitute the initial condition. So, let us try substituting the initial condition. The initial condition was at time t equals 0, Ca was 2. So, let us try to do that. At t equals 0, what would happen? You would have Ca naught would be equal to 7.5 minus 5.5 times exponential of 0. So, this would make the equation to be Ca naught equals 7.5 minus 5.5, which is equal to 2 moles per liter. So, we are able to verify and get the correct answer. So, that it means that the equation we have, which is the correlation for Ca as a function of time, is accurate. So, the last part of this problem is to plot the curve. So, let us try to plot the curve. So, this would be Ca in terms of moles per liter and this would be time as time goes here. So, let us mark the points 2, 4, 6 and 8. So, at time t equals 0, Ca is equal to 2. So, from here if we were to plot the curve, it would look something like this, where it plateaus off at 7.5 moles per liter. So, that is the maximum concentration you would be able to get, because that is the steady state concentration which we calculated for at time t equals infinity. So, with this we have solved an unsteady state material balance problem. So, we will continue in the next section where we talk about unsteady state energy balances.